So, starting off with this question. When we're looking at these formulas, number one, these formulas, to be fully cognizant of what you're wearing, what you're looking at here, are a direct result, I guess, of what's the dude that invented the printing press? That guy. Right? Typewriters, computers. That is the only reason this exists, is this format. Because if we're trying to, you got to think about what chemists have to do. We had to transfer this knowledge. I learned something about this structure, and I can transfer that knowledge across country. The best place to transfer that knowledge is through paper. Right? We have put it in an envelope and I ship it across the country. Right? And eventually someone gets it. Right? And if we're looking at printing presses or typed things, I have to have it in a typed kind of format. Drawing out the structure was not easy to do even 20 years ago. Right? The drawing of structures has increasingly become more and more valuable and useful and facile to the point where being able to interpret this kind of language or format of structures, I think, is going to disappear, right? As it should. Right? But we aren't there yet, which means you have to deal with it. Right? If we think back to kind of where this is starting, we're looking at it as a written language. We read by default left to right. So the very first thing that you should be doing is starting at the left and slowly working your way right through this. Right? And now we've got a fun question for you all. What's the first thing you encounter? Right? And depending on whether, did I already have a conversation with you? Yeah, that's not fair. You shouldn't have answered. Most people go, oh, well, I see a CH3. No, you didn't. What did you see first? Parentheses. Focus on the first thing you see. I see parentheses. How many parentheses should I have? 2. That's what the subscript tells me. Okay, so I have 2 parentheses. What are those parentheses connected to? Now I'm continuing to read. They're connected to that orange C. So I want to show my bond to that orange C. Okay, now what's connected to that orange C? I can continue to read left to right. Oh, I would encounter an H. I'm going to draw it as orange. So there's my H. And here's where I would argue the next kind of major mistake comes into play, is people go, oh, we just read left to right, which then means that C is connected to the H. And I've seen that on lots of people's stuff. Don't feel bad, it just happens. That doesn't exist. Hydrogen can only form one bond. So one of the lessons that you should pick out of drawing Lewis structure are what are the common bonding patterns for each of the individual elements. Once you know the common bonding patterns, you know not to make that mistake. And what they're actually saying is that that C needs to be bonded to the orange C. Okay? Now what's connected to the black C? The black C, huh? Sorry. And NH, no. N, no. Parentheses. Okay? Again, follow the language all the way through to that brutal detail until you get used to those patterns. And maybe you're already used to those patterns. You're like, oh, it's this thing. Slow it down. Okay? Parentheses. Okay? Those parentheses can be there to help kind of segregate the formulas off, so I would take advantage of those. Those are saying that that C is bonded out to that parentheses. So now the question is, what happens to that CH2, CH3?
It's bonded to the black C.
That goes back to the black carbon. Okay, that's what those parentheses are supposed to be kind of helping with, is segregating that information out. Do you need to have that context there? No. And that's where things could get dodgy. Let's say you bonded it to the parentheses. Okay, what's in the blue parentheses? It's actually a strong argument you didn't need the blue parentheses at all. What's the first thing within it? A carbon, which is?
Has 2 H's.
Bonded to 2 H's. What's the next thing? Another carbon that has to be bonded to that carbon. Why does it have to be bonded to the carbon? 2 answers.
Because they're both in the parentheses together.
3 answers. The blue carbon needs its octet satisfied, so it makes sense to connect the red carbon to it. What's the other answer? Can I put the red carbon to the hydrogen? No. Okay? What's that red carbon connected to? 3 hydrogens. Of course, the parentheses are going to get in the way, and we'll try and redraw it here in a second to clarify those. Okay, so we could try that. Okay? Now we've got some potential problems that we have to deal with. Okay, what problems do we have in front of us? Okay, we've got a problem with our black carbon. What's the problem with the black carbon? Doesn't have a proper octet. Okay? What other problems do we have? The other problems are easier problems.
The nitrogen and hydrogen.
Rewind back just a hair. What nitrogen? My drawing has no nitrogens. What's the problem that you're fixing? What the hell's in the parentheses?
Yeah.
What's the hell in any of the parentheses? There's a bunch of other problems. We got to fix those problems. Okay? So which problem do we want to address? Okay? I'm already hearing that nitrogen, so let's go ahead and take a look at that nitrogen. It's going to be real hard to address that black carbon because I don't know what's connected to it because I have a green parentheses. So what's in the green parentheses? A nitrogen. And a hydrogen. What's the hydrogen connected to? The nitrogen. Okay, so I could back those parentheses out. Oh, I got a stupid fat eraser here. Okay. Is my nitrogen happy?
No.
Why not?
A lone pair.
Okay. Okay. And 2 people just jumped in with like right off the answer. Okay. People that are struggling with it may be wondering what the hell they're talking about. First off, nitrogen is missing its octet. That's a problem that needs to be addressed. Okay? How is it missing its octet? This is going to come back to the common bonding patterns for nitrogen. If you do a bunch of simple practice, this is not simple for the record, and we'll come back to that. If you do a bunch of simple practice, what you will learn is that there are common bonding patterns for each of the elements we worry about on the periodic table. And you're like, I got to worry about 118 periodic elements. No, you should go back and watch the very first lecture, because what do I say in the very first lecture? We erased 90% of the periodic table, and we're left with like 10 elements. Those are the only elements we really care about when it comes to bonding patterns. Which means, do practice on those so that you know all the common bonding patterns. Or cheat and hope somebody gave you a list of all the common bonding patterns. Slide 30. Okay? And it shows up multiple times because they have to keep reiterating, you need to know this. Okay? So if you want to kind of end run that, you can. Just realize you're now weakening your strength in what those common bonding patterns are. Make sense? Okay, and we look at the common bonding patterns for nitrogen. It should have 3 bonds, yes. And it should have a lone pair. We don't have the lone pair drawn, so we could go through and tag that lone pair on there. What does that fix for us? The octet. We don't have to worry about the octet on the nitrogen. Great. Everything's fine and dandy. Okay, we could go back and look at the red atoms, or the red parentheses as our secondary problem, but I'm going to argue we can skip that and go back to our black atom as a problem. What's going to be the problem with that black atom? Octet. Okay? And I have no way of fixing it with the drawing that I have. Okay? For some people, well, can I make a double bond? Okay? Yes, and we talked about we did talk about curved arrows, right? Moving electron. Okay, yeah. I could take the lone pair on that nitrogen, move it down, and I could make a double bond between the nitrogen and the carbon. Does that satisfy the octet on the carbon?
No.
No. Is my octet still satisfied on the nitrogen?
Yes.
Yes. Is my nitrogen neutral?
No.
Does it matter?
Not really.
Gray area. Okay. For our drawings, what we're trying to do is test, do you understand how to draw a structure? Okay. Within that, we probably are going to pick neutral structures because those are a little bit more straightforward to deal with than charged structures. Okay? So that's a little bit of a curveball that could help us. There's also some more information that would suggest that we shouldn't be drawing any charged atoms. What's that more information? What formal charges? all atoms. But where do I see all atoms? Where would formal charge get written? They would get written onto my drawing, not into my structure, or not into my formula. Where is formal charge written in a formula?
Top right.
The top right. Do you see anything written in the top right? No, which means the charge is neutral, which means that nitrogen cannot be positively charged. Okay? So what does that mean? That means we drew something wrong. What did we draw wrong? The blue carbon should be connected to the black carbon, not to the nitrogen. That eraser is killing me. Okay? And this isn't an is what it is. I heard you. Okay? What it is recognizing the common bonding patterns for these structures, and there's only certain ways that logically make sense to satisfy it. Okay? What car door do you get in when you enter your car? The driver's side? What if you're not driving? Any other door. Okay, you are driving, but the driver's side door is broken. You can get in any freaking door you want, but there's certain aspects that make more logical sense. If you see somebody getting into the passenger side and then climbing across to the driver's side, you might be calling the cops. Okay? Because that's a weird scenario. Exact same thing is happening here. There's certain common patterns. You have to recognize those patterns and follow them. That requires practice. That's painful. I get it. But that's what you need to be working through. Okay? That fixes the black atom. Go ahead.
My question was, I thought that if you had a positive and a negative within the drawing, then it cancels out to be neutral.
Yes. So there are scenarios where you could have a positive and negative in the molecule. The overall molecule would show a neutral charge. I would hope, though I can't guarantee, because I haven't looked at all however many different sets for this particular question set, okay, that none of those show up as draw the Lewis structure for this. Is it possible? Yes. And we will see those. Did I create another problem by fixing the black atom?
You left the double bond, but it needs a lone pair.
The nitrogen needs its lone pair. Do I still need the double bond? Yeah, why do I need the double bond? The octet, both on the nitrogen and the carbon. I have some context to explain why the double bond is coming into existence. Now that I've resolved problems 1 and 2, I can now backtrack and say what's in the parentheses. Right? Well, what do I have within the parentheses? The red parentheses. I have a carbon connected to 3 hydrogens. I know that carbon must be connected to another carbon with 2 hydrogens. I heard someone say this is fun, and I'm not quite positive I'm trusting you're saying this is fun, but it should feel kind of like a puzzle. Most of what OChem is doing is coming up with puzzles to figure out how to understand what's going on behind it. It is a little bit challenging, but all puzzles are. Okay? Generally speaking, what I get from most students is that they absolutely loved taking this class. They thought it was a fantastic class. They really enjoyed their time in it. They hated every minute of an exam. Yes, I hate every minute of the exams too. Okay? I have an extra one. I hate every minute of trying to assign grades at the end of the semester. Okay? Work on it as a puzzle. Try to make it more enjoyable. That will improve the time that you spend practicing, which should improve your overall performance on exams. Make sense? We could finalize that last piece, right? Okay. I believe this question was probably something that came up with one of the quizzes, because I'd be surprised if you just did this on your own. Okay. So now that you've done the work, okay, so now what we'll do is backtrack a little bit. Because I said we wanted to walk through an example. We walked through the example. Ta-da, there's an example. Hooray. Okay. Why are we doing this? Well, we're doing this because we have to prove that we know how to interpret these structures. To prove how we know these structures, we have to go through and take a quiz. That quiz needs you to draw structures. Can you draw structures in Canvas? No. Okay? And the extra irritating thing with OChem, which works to all online homework systems as well, is that you have to be very particular about how you draw things. Okay? Remember the examples that we did quickly in class? I asked, Were these different structures? You're all like, yeah. And I said, no, they weren't. What? There's some context missing that you don't know. You have to apply that knowledge into the system to be able to explain what's going on with it. A computer could very easily look at those two drawings and say those are different and wrong. Okay? Or equally agree with you that they're different because it can't interpret that second layer of information, at least yet. Okay? We're doing better at it, but we still have problems with it. Okay? So you have to find a computer system or a computer drawing system that allows you to be able to draw these structures out and manipulate them. That's what Smiles is supposed to do. It is a free system. Okay? And because it's free, it sucks. Yeah. It's just generally how it works. Okay? You only get good things if you pay for them. Okay? Even then, sometimes it sucks. Okay? So the point of Smiles is to take this information and to turn it into a drawing that can now be graded, or a code that can now be graded. Okay? Kind of makes sense? Within that, what do you need to show? Do you need to show hydrogens? Do you not? How do you know? How do you know? There's two answers. What's that? True, you could go back and be like, I'm trusting that all the simplifications that we make within OChem hold true. Do you like trusting? Okay. What?
You just do it.
You just do it. You enter it and see what happens. Okay? There's another way. It's really simple. Several of you did it. What's that?
Read the directions.
I don't know that the directions actually provided context in this case. It's possible. Sometimes, yeah. You email me, well, what the hell was this? Oh, okay. I don't know, let me look at it. Oh, dang, yeah, this is kind of, well, yeah, I could do this. Well, can I do this? Can I do that? What happens with the information? So what I went through and did is drew this structure. Then what did I do? I deleted all the hydrogens. Did the code change? No. Okay? Because the code didn't change, what does that mean?
Implies hydrogens.
I don't need to worry about drawing all the hydrogens. If you're playing with that software during a quiz, are you thinking about, do I need to draw this or not? Let me check the coding and no. Okay? That's an entirely different mindset. Leave that to someone whose job it has been to break things. Okay? Let somebody else do that. Make sense? Do we need to show my... sorry. Do we need to show the Smiles walkthrough?
Please.
Okay. For those people that are asking for it, I will absolutely show it, but what I'm also going to do is say, did you know that I already did a walkthrough? Okay. But not in that one. That's just the links to it. I've also been hearing ChatGPT this, ChatGPT that, and I was like, sure, cool, that sounds good. Let's try and use it. It's going to be pretty awful. So, we click this link, and we should get something that's probably going to be wicked small within the screen. There's a bunch of stuff on here. Just because there's a bunch of stuff doesn't mean you have to do anything. Which of those things do you think you need to do anything in?
Top left.
Okay. Top left, where we actually have little buttons and tabs things. Those buttons and tabs should look familiar. They should look kind of similar to what we do for smart work. Okay? So, I don't remember the drawing. I think I did. CH3, CH2, carbon. Nope, come on. Let me draw. Fine, I'll do it this way. More than one way to skin a goat. Or is it a cat? I like cats better than goats.
Yeah, that's probably important.
Okay? We can put a nitrogen there. And I go, oh, ta-da, I did it. What's wrong? Say again? There are too many hydrogens. What else is wrong? No double bond. The double bond, I would argue, is probably the most important thing. What I would do, based off of my training with smart work, is I tried to hover my mouse over the top of that single bond to turn it into a double bond. Oh, come on. Dude, you just did it.
You should time this for 5
Oh,
minutes.
son of a gun, it did it. It didn't do it for me the last time. I was like, oh, I got to manually do it. So it must just be the size of it was too small for for when I first did it and I couldn't get my mouse to hover over the bond, it kept jumping on the atoms. So I said, okay, screw it, went to the double bond. How do I know I have a double bond? Because there's 2 lines versus 3 lines. Okay, so I click double, click, jerk, whatever. Just gonna put it out there. And we've got the double bond. Does that make sense? So let's push again. This is quiz format. Everybody goes, okay, it's a quiz, which means what do I need to get for the quiz? True, but how do you get 100%? You have to get the answer. So your immediate reflex every time you take anything that's associated with time and points is what is the answer as fast as humanly possible. Okay? Fun part with that is you're doing all of your work in your head. Well, there's nothing wrong with that. I've done work in my head all the time. Okay, do you want me to be able to read your brain? Any point in time, I can hear what Gavin's thinking right now. That'd be great. At some point today, you're going to have drunk enough water. Where are you going to go?
To the bathroom.
You really want me to hear inside your brain? Right? Should have had some more fiber. Right? Like, those are conversations you don't want me to be part of. Right? Your brain is a very scary place. This is why most of us don't talk. Right? Right? Where we hold things back. Okay? Your brain is freaky, psychedelic, and nasty. No one wants to be in there. Why the hell are you spending your time every time you take a test answering all of your questions in that scary, nasty place? That is an awful, awful strategy. Stop it. Write it down. Okay?
So what's stopping you or us to take a picture of what we've written down and just submit it?
Sorry.
So
I didn't record it.
I think that would just add more for him writing-wise, but also I wish that it was the case because Smiles.
Isn't that bad. It really isn't that bad, guys. Okay. So, is there anything that stops me from doing that? Absolutely not. Absolutely not. Okay. And have I worked around that? Yeah. But I would argue the vast majority of people can deal with this and should be able to work with this because smart work's going to make you work with it too. Okay? So if you're one of those people like, I guarantee it's Smiles' fault, it's not mine. That has not been the case on anybody I have asked so far to show me their work is wrong. Sorry, it's not Smiles, it's you.
I think also part of it is just that Smiles is like less intuitive than Smart Work.
It is.
Which means like it doesn't automatically add the charges or stuff like that. So like Smiles is the one doing that, but it's more like an indication that we don't understand something. Yeah. And we have to like be
Well,
careful.
and that's why, for the people that have submitted questions and complaints to me over this weekend, what was the first thing that I asked? Show me your work. Show me what you've got. Because if what you've got is good, that's Smiles' fault. Yeah, I can work with you. If what you've got is bad, it doesn't matter how bad or good the interface is within Smiles, what you have is wrong. You're shifting all of the blame onto a system that isn't at fault. You can shift it on me, I'll accept that one. That's fair, but don't shift it to Smiles in that respect because you didn't understand what you were doing, which is okay. Why is it okay that you didn't understand?
It's the second week of the class.
Yeah, it's the second week, man. Give yourself some leeway. Give me some leeway. We gotta learn a whole freaking language. Right? So spend some time to slow down and just kind of acknowledge that you don't know yet and build from it. I'm sorry, you had your hand earlier. No, I answered it.
This is the second thing. Residents in Smiles. This was kind of the death of my hope in life.
So the caveat I can do with that is number one, we'll have to stop the recording. So let's go through. Okay. For the record, that's a CL, not a U. Stop giving me a hard time. Okay. Some common things that we want to watch out for. When we do resonance, what are we moving?
Electrons.
What electrons? Okay? And now we're going to run into some language issues, some kind of backup problems that we have to deal with language, okay? Particularly when it comes to resonance. Okay? There are only two types of bonds. What are the two types of bonds? Sigma and pi. If you've been watching the videos, hopefully you're catching up with that. If you haven't watched that, you might be like, aren't there three? Single, double, and triple. That's non-existent. That's utter nonsense that doesn't exist. Sigma and pi. Officially, sigma and pi doesn't really exist either, for the record, but it works for the class, so stop it. Okay? So we have sigma and pi. Why is that important? Well, when we do resonance, what we're allowed to move are pi bonds and non-bonding pairs of electrons. That's it. Okay? Pi bonds aren't necessarily a problem. They're a little bit easier than non-bonding pairs because pi bonds are shown, but are they shown differently than sigma bonds?
They're either double bonds or the third bond, because if you move a sigma bond, then it breaks the
Okay?
bond.
So to your statement, which one is the pi bond? The green one or the blue one?
Good thought. Doesn't matter as long as one's left.
Therein lies the issue. There is no signifier that allows us to say which one is necessarily the pi bond. Okay? As long as we have two lines, one of them is a pi bond, it doesn't matter which one we move. Okay? They have the same identity, the same characteristics. So at very least, a pi bond has been identified, so we could go through and move it. Okay? Because we're looking at resonance, we also have to be aware of
Balance. Or the lone pairs.
lone pairs.
So those are implied too?
And lone pairs are extra nasty because they're implied. Where are they implied?
On the atoms.
They're implied on heteroatoms, which means not carbon or hydrogen. They're implied to satisfy octets. I have an oxygen atom and I have a chlorine, which means both of them have lone pair electrons. How many electrons are around the oxygen right now?
2.
4. Each line represents a pair of electrons. Okay? Not sure I believe that's what you were going with, but I accept that. Okay? Okay? And I would avoid the use of pairs for dealing with formal charge calculations, because most people say pair and they start to goof that calculation. So they're non-bonding electrons. We go through and look at the chlorine. How many electrons are currently shown around the
6.
chlorine?
6.
Currently shown around the chlorine. 2. The line. God, many Christmas. Which means we need, that's why I said shown.
6 unshown.
Yes, there are 6 unshown. I don't even know what that means. Okay, so now we have 8 electrons. Okay, because we were already saying we were nervous about dealing with hydrogens, we should also go through and imply hydrogen, or not imply hydrogens, so be explicit with those. However you want to show them is okay. I have seen students go through and just show the little chicken foot. Okay, problem with that is that could start to imply carbons. You certainly can't do that in smart work. Okay, you probably can't do that in smiles either. In fact, I know you can't do that in smiles, so be careful with that notation. On an exam, you're relying on my mood, so don't do chicken foot either. And then we also have that hydrogen there. That hydrogen is probably the most commonly missed, and I would argue that's why you made your mistake.
Double bond.
Okay? And so if we now go through and look at this, okay, particularly in resonance, this structure now provides a whole lot more context than the initial structure drew up. Because when we look at the initial structure, what do you see needs to move? The double bond. And you immediately reflex to moving the double bond somewhere. That becomes the problem. Okay? Let's walk through where we should move those electrons. Okay? Because the electrons are in the double bond or in our pi bond, they can really only move 2 directions. They can either move towards the oxygen or towards the carbon. Okay? If we move towards the oxygen, there's really only one space to go. It has to go to a non-bonding pair. If we move towards the carbon, we could go to the carbon atom, we could go to the bond, or we could go to that bond. Everybody see that? All of those are fair ideas. Whether they're correct is a different option. Okay? So let's first address the red versus blue, just as bullet statements. Where should those electrons go? Towards the oxygen or towards the carbon? Oxygen. So right out of the gate,
I should just went to oxygen. Boom.
okay, you've already moved them the wrong direction by moving them down towards your carbon. Your first arrow should be moving them up towards the oxygen.
So is this a useful?
We're going to cross that bridge. That's why I picked this. Why it was an awesome example for you to throw at me. Okay. So what does this mean? What would our drawing look like if we followed these instructions?
It'd be one bond instead of two, but also we would have to put a negative on oxygen to be charged.
Can I get lazy and not show a bunch of stuff?
Just write a negative.
Pretty sure you don't want me to just write a negative and say I'm done.
Negative right next to the O, the oxygen, right there.
Okay. Right? Okay, and then we'd say negative on the oxygen, because the oxygen has gained electrons, right? Absolutely, it's negatively charged. Okay? Remember, we still have the electrons on the chlorine. Okay? This is something that we could play with smiles again and be like, we could try it once, oh, I got it wrong, but I've got some questions. Do I need to show the lone pair electrons explicitly or not? I don't know. I haven't played with it yet. Okay? So we can say, okay, we enter this in, we get it wrong, send Mike an email. Mike, the system sucks because I drew a perfect structure. Your structure is wrong. What's wrong with it? So this is one of those common mistakes that, again, happens with resonance. Okay? The big red flag that can help us with this is that in resonance, all you're doing is moving the electrons around the molecule. You do not remove electrons. You do not add electrons. They stay constant. And if they stay constant, what should happen to the charge? Should stay constant. And if I look at the overall charge for my first molecule and my brand new resonance structure, I would note they're different charges. That's because I didn't draw a resonance structure. I provided lovely curved arrow. I love that. That's fantastic. But you didn't follow the directions that your curved arrow stated. What electrons moved? Pi bond. Where was the pi bond?
The carbon.
Carbon and the oxygen. So that was two electrons, because it was a bond, shared between oxygen and carbon.
So the carbon's charge is positive.
When the electrons moved up to the oxygen, you stopped sharing with the carbon. The carbon has now lost an electron. And if I lose something that is negative, I become positive. Or, if I'd spent the time to draw on all of my implied hydrogens, I would have also noted that this carbon is missing an octet, and I should be addressing its charge accordingly. Did I do all the common bonding patterns and have those memorized? A carbon with 3 bonds is positively charged with no lone pairs? Yeah, if I got that, ta-da, I now have that memorized. The instant I drew it, I knew what happened. That's why that common bonding pattern thing is so flippin' valuable. You have to know those. Okay? So cool, we fix it now. And in the response that I gave you, I was like, resonance is your problem. You need to go back, you need to consider implied hydrogens. And what that means is a result for your structure. And I'll probably throw in, if you just moved electrons around, charge should stay the same. Okay? But I will also say, before you try again in Smiles, you need to send me an email of your result. So you send me an email of this result, and I go, that's lovely, you did a good job showing your electron motion. It's fantastic. Smiles is going to tell you you're wrong. So, what's wrong?
The octet of the carbon is not satisfied.
Okay. Rule number 1 with all Lewis structures is your octets must be satisfied. Okay? Do you have a satisfied octet? Nope, so that's busted. Yes? Pause. Yes. Could we move a lone pair? Yes, we have to satisfy the octet. So we could move electrons from the oxygen down into that bond to satisfy the octet. But then what did we draw? The exact same thing. Okay, and this is where resonance comes into play. What other electrons are accessible to me? I also have the chlorine. I could take a pair of electrons from the chlorine and shift them that direction inwards. What is the resulting structure? I now have a double bond to my chlorine. I've lost a pair of electrons on the chlorine because it's now in making that double bond. Okay. I didn't forget that my oxygen was negative, and now I say, ta-da, I did a good job.
Chlorine is positive.
I have to know the chlorine is positive. How do I know the chlorine is positive?
So,
Cool. I absolutely love the example that everybody shouted out. It just lost electrons. How else do you know it's positive?
because the neutral would have six electrons and then one bond.
I think I'm accepting that. What I believe you're referencing is that you've memorized the common bonding patterns for chlorine. You mean that little sheet where you had them? Yeah, there you go. How else could you figure out the chlorine was positive? There's 3 ways. At a minimum. How else do you figure out chlorine is positive?
Is that what it's called?
I would call it formal charges, but that's fine. Chlorine has 7 valence electrons minus the 4 non-bonding pairs minus the 2 bonds gets me a +1. All of that works. This is why drawing out structures can get a bit dodgy to figure out for students. Is depending on the path that you're taking, you can get to the same answer different ways. What way is working for you? My job is to set it up so that you have these options, and you have to decide the way that works best. How do I preference? Arrows every day. Use the arrows. Know what the arrow means, solves everything. Why use the arrows? Because the arrows are going to show up for the entire rest of your career with OChem. Learn them now. Who's given this one?
It's saying that would be my.
That's the last bridge we're going to cross. Okay, so now what? So now what do we do? Are we at the point where we can enter it into smiles? Yeah, I would think so. And so what are you guys mumbling about? Let's, bring the whole secrets are evil, right?
Is this useful or a mess Lewis structure?
Okay, where are we at with figuring out what our Lewis structure should be? And this is one that I really honestly don't know how to play it with smiles, and it may very well be that resonance is one that I just give everybody credit for. I honestly don't know.
What did it just?
Because
The original one?
we've got 3 resonance structures drawn up here. If the question is, what's the best one? Well, what's the best one? Why the first one?
It doesn't have charges.
This is the best because it has charges. It doesn't have charges. Do better because charges is actually the second thing.
Because it's not reactive.
Nope. They are all of these represent the exact same thing. This is the motion of the body. Okay? We're just looking at a freeze frame saying Mike's hand's up here or Mike's doing a handstand. Okay? They all exist. What's the number one reason why that top structure is best?
Contacts are all satisfied.
There it is. Octet. Okay? That one's the best. So is Smiles really asking you to draw the exact same molecule? I don't know. I would actually have to drill into that quiz question to see. And we can pull that up, just not record it, but we can pull that up, take a look, and see. I would bet not. Okay? Because if it's asking for resonance, what should you do? You should do some resonance. Okay? But now we enter a different dilemma. If we are now forced saying, well, it probably doesn't want me to just draw the structure again, because that's kind of boring. I got to draw a resonance structure. Which resonance structure do I draw? Why do we want to draw the third one?
The first rule. Octet.
First rule says octet. I would argue this is what you should be drawing. Okay? This last one. Should I draw that one?
It has a better charge area.
We like the charge distribution a little bit better, but we have an octet. Which rule trumps, octet or charge? Octet. So this is the least likely. That's an A in there, I think. Okay. Is that gray area? Yeah, it is. What does that mean I'm going to be doing? I'm going to be scrolling through SpeedGrader looking at that question. What did you draw? And I'll look at it and go, what did you draw? Oh, you didn't draw anything. I got to copy and paste. Read your structure. Yeah, your structure looks good. No, your structure looks like trash. You deserve to lose points. Make sense?
Should we go over another one?
Sure. I didn't look very exasperated.
That was the original. Which one's that from? The same rules. Business? Yeah. What'd you get on the read? 50.
Another resonance. This one, I think, fits the pattern of this is a good question to ask. This actually fits better in that category. Why is this one a good one to ask?
You want to get rid of the charges?
We've already got charges built up in this structure. It is very likely that we should be able to move these electrons around where we get no charge. Okay. When we do resonance, what do? When we do resonance, what do?
Check for the implied.
Lone pairs, so it's what are we targeting? Lone pairs and pi bonds. So we could identify our pi bond, and almost universally people are going to jump all over trying to move that pi bond. Before we start dealing with the pi bond, let's make sure that we don't have any other lone pairs that are potentially questionable out there. That carbon is positively charged. How many lone pairs should it have? None. How do I know it has none?
Because 4 is the
First option I would argue is we go straight to dealing with that chart. Okay, dealing with that chart, if I have a positively charged carbon, I know it has 3 bonds. There's an implied bond to a hydrogen. Okay? It has no lone pairs. If I wasn't convinced, I could say carbon has 4 valence electrons minus the number of bonds. There's 3. We have that implied hydrogen. Okay? Then minus the number of non-bonding electrons. That must equal 0. Not 0, number. Positive. Why does it have to equal positive 1? Because it says it's positively charged. So what does that question mark need to be? It needs to be 0. There cannot be any non-bonding electrons on that atom. This is building with those processes and understanding our common bonding patterns. Getting it? Slowly seeping in. Okay. So no lone pairs on that carbon. Do I have lone pairs anywhere else?
Yes.
Yeah? Where do I have them?
On the nitrogen.
Cool, on the nitrogen. How many lone pairs do I have on the nitrogen?
2. So you're missing out.
And I just fell into that trap that I said we shouldn't do. We should be counting the non-bonding electrons. Okay, so there's 4 non-bonding electrons or 2 lone pairs. Okay, so cool. Where should I start my resonance?
With the nitrogen, because it's not the ideal bonding shape pattern form.
I would argue, yes, we should start with the nitrogen, but not because of the bonding shape pattern.
Bring electrons from negative.
It's all about moving electrons from a source to someplace that lacks. Where's someplace that has a lot of electrons?
The tartars of the pipeline.
How about the atom that has so many electrons, it is literally negatively charged? The pi bond is a source of electrons, okay, but it's occupied already within the bond. Okay, is it going to be wrong? No. But if you start with that nitrogen, that can help dictate how everything else moves. So where do I want to move them? I want to move to make a double bond with the hydrogen. No, okay, sorry. Move them to the carbon?
No. Double bond.
I can't move them to the carbon. I have to move them to the bond in between. Are those two arrows different? Yeah, they are very, very, very different. Smart work will rip you to shreds. Okay? Handwritten is one of the reasons why I actually like smart work, because handwritten, you put it in a gray space. I'm like, I don't know what you're trying to do. Do I want to start a fight? And I'll move on. Smart work will do all the fighting for me. Okay? And it can be very, very important content-wise where those electrons are moving. So cool, we move it there. Okay? And this is an interesting one. The last one, we actually didn't have this dilemma. Can we go through and draw the product for this?
Exceed the offset.
Okay? So yes, we can go through and draw the product for this, but as is very clearly getting pointed out, we exceed the octet. What we're saying is we make a double bond between the nitrogen and that carbon. We still have a lone pair of electrons. Okay? Which means, does this structure exist? No. Exceeding the octet on carbon is 100% disallowed. You are never, ever, ever allowed to say that that is an answer. But what I can do is cross it out and say, Mike, that's not an answer, but it gives me some context about now what can I do. The problem is that I've exceeded the octet at that carbon, which means I have to move electrons away from the carbon. The only electrons that are allowed to move when I've exceeded the octet in this fashion would be our multiple bonds, our pi bonds. Do I have multiple pi bonds to choose from? Yeah. I can choose the one I just made. That's pretty boring because that takes me right back to where I started. Or I can take the other one. Okay? Where do I want to move it? My recommendation would be to move it as short as humanly possible. So I want to do something like that. I'm going to go from the bond to that atom. Okay? You can give side eye later. Don't worry about it. Okay? I'm adding instructions on this drawing. Is that allowed? Does this structure exist? No. I'm adding instructions on what to do on something that is not physically there. So you open up your IKEA box and they give you instructions on no paper. And if you're like, that doesn't make sense. Yeah, exactly. It makes no sense. You can't draw instructions on something that doesn't exist. Which means, where do those instructions need to show up? On the first structure. Which means when drawing our resonance, we aren't excluded, precluded, included to just one arrow. We can use multiple. Okay? What does this mean? That structure doesn't exist anymore, and now I need to go through and redraw it. And are you shaking your head at me because you don't like what I just did, or that you don't like that this isn't the answer? You shook your head at me. I was watching.
It's supposed to be a double bond and not, because doesn't that entail that it's supposed to be a lone pair on the carbon?
That means there's a lone pair on that carbon. Yes. Awesome. What else is wrong with my drawing? Say again? I did nothing to the carbon, the positive carbon, so it's still positive. What else is wrong with my structure? There's no octet issues with any carbons. All the octets are perfectly satisfied. Well, except for the positive carbon. That carbon that we just put a lone pair on is now negatively charged. What happened to the nitrogen? Became neutral. We started as a negative. We've lost an electron in that sharing process. We go from a negative, losing a negative becomes more positive. It doesn't mean it's positive. It means it's neutral because we started negative. We're only moving one electron. Kind of, sort of? Cool. This is what I could go through and draw. Is this a structure that you didn't like? Yeah. Why do you not like this?
Because I want the lone pair to go to a double bond to neutralize both sides.
What happens to the negative carbon? Becomes neutral. It has shared electrons with that other carbon, making the new pi bond. What happens to the positive carbon? It is also neutral because it has gained electrons in the process of making that pi bond. So when we look at that starting structure that we were working with, how many resonance structures should we be looking at? 2 other options. Which of those 2 options should we be providing as our answer? We should be providing the third one, the one that I did not stop at, or that I intentionally avoided. We should be providing that one as our final answer because
Octets are filled.
octets are satisfied. Thank you for that. And, sorry, we got rid of the formal charges. Does that make sense? Should we do a little mind bend? It's just a small mind bend. I'll take that. Oh, okay.
Sorry. But in the lecture video, I mean, I know you were probably showing this so we could understand it, but why didn't you just draw the orange arrow bond to bond? Because you said we could do that.
Okay. This is all going to depend on what you're trying to do. In a lot of cases, what you're trying to do is find all possible resonance structures. And if you're looking at a scenario where you're trying to find all possible resonance structures, the more bond-to-bond actions you do, you increase the likelihood that you're going to skip a resonance structure. Okay? Potentially a valuable resonance structure. So I would encourage you to at very least think shorter hops. Okay? At least initially, I would push that further and say you should draw these shorter hops. Okay? But you're right, when it gets to a final answer, wouldn't it make sense to go directly between those 2? Sure. How does my drawing change?
Just so the green arrow stays the same, and then the orange arrow moves from bond to the bond next to the fossil carbon.
Very subtle difference in where those electrons are moving. Okay? And that can take us directly to that other structure, which is a fun little bit of information. If you have 20 resonance structures, you can add arrows to go from any one to any other. That's the point of resonance. Okay? You may need a whole bunch of resonance arrows, but you can do it. That's the point of recognizing how the electrons can move and shift around the entire molecule. You need a little bit more flexibility within those systems. Okay? For the sake of speed, I'm going to say it's going to depend on the question. If you're looking at this and being like, if I just do that one little hop, that's awesome. You just started to play chess. Okay? You realize what the next move would be. That's exactly what you need to be doing. Where are you right now? I don't know. You figure it out. Okay? Slow your hops, and once you start to realize that you can start extending how those electrons move, by all means, start skipping. But the instant you start skipping and getting wrong, that's when you're going to have me be like, what did I tell you to do?
So in this instance, because you said it depends, is the second structure, it's not the best because the octets aren't satisfied, but is it still a valid structure?
It is still a valid resonance, and this becomes the big overarching issue, I would argue, within resonance. When we first start talking about resonance structures, we try to make it like this, oh, there's only the best, and we only look at the best, and it's actually wrong. We don't do that. We very often look at the first worst, is how I call it, okay, or second best, because the second best gives us some information about where our structure is going to react. The best resonance structure hides all of that information. So if I go through and look at that bottom right molecule, how would I predict this molecule to react? Right? For a reaction to occur, you have to transfer electrons from one atom to another atom, which means you need a negative and a positive. I can look at this and be like, well, I guess the nitrogen has a lone pair, maybe. But if I look at this top one, what do I see? I see a screaming missing octet. Dude, that's going to be where it reacts. This molecule is going to react as a positive. It's going to want electrons from somewhere else because it's missing an octet. How do I know it's missing that octet? Because I did all of the resonance to allow me to see that. Where did I do all of that resonance? In your scary, freaky little brain. Eventually, you can transition from paper to your brain. You're not there yet. write it all down on paper. By the time we hit second semester, that's a functional group that would show up in second semester. You would be acknowledging this molecule, but seeing this. And running chemical reactions with this acting like that. That's pretty cool. Like that's not that far away, guys, and you're gonna be awesome. No one okay. I think you'll be awesome. Next. When do we end? Are we 12:30? 45, okay. How are we feeling? Another?
On the sentence structure, is the octet not wrong because there's an implied hydrogen, or
That carbon is still missing its octet. If we look at this carbon, you're correct. It is not missing its octet. What is octet?
8 electrons around it?
8 electrons. The positive carbon only has 6 electrons around it. The negative carbon has 8. It has the same 3 bonds, but it now also has that lone pair.
So is the third bond an implied hydrogen, or?
Yep. Okay, which becomes a fun one. There is an implied hydrogen here. How do I know there's an implied hydrogen there? Because there was an implied hydrogen to begin with. Because there was an implied hydrogen to begin with. Okay? So those charge structures can be really hard to nail down, those implied hydrogens. That's where I would look to the neutral structures to tell you there's a hydrogen there. That's one of the things we started at the very beginning. If you're uncomfortable with recognizing implied hydrogens, what I've drawn up here is nonsense for you. What does it need to be? Graphic. This is what you would need to see if you're struggling with implied hydrogens. Every single one of those hydrogens needs to be shown in every single one of those steps. Do you like doing that?
Well, that first structure, there's 2 hydrogens as well, right?
2 hydrogens to what?
And that's carbon that's straight up from the bond from nitrogen.
Where?
Wait, like here.
There?
Yeah, like here, there's 2 hydrogens, right?
Good question. Let's bring it to the crowd.
Oh, no, because there's...
Tough. That carbon, how many hydrogens are connected to it? And don't be looking at it, well, you only drew 1. I don't care what I drew. How many hydrogens should be there? Ask that question. Put all the words you can to it.
Ask a question?
Yeah, you said is the double bond.
No, I said because of the double bond.
What is the double bond?
It's the 4th one.
The double bond is 2 lines. What does a line represent? 2 electrons. So a double bond is 4 electrons. Plus that remaining single black one gets me up to, with my head, okay? Which means I need 2 more electrons. That has to be just 1 hydrogen. Does that make sense? So the multiple bonds do get tricky, and a lot of that falls back to how you're classifying them. I would argue if you're making that mistake, what you're classifying them as is a double bond. Double bonds do not exist. They're sigma and pi. Make sense? Other questions?
Yeah, I had a hard time with the functional groups.
Functional groups is going to be an interesting one. Trying to think of the best way to walk through that one. And that's one, again, it's going to depend how many different systems are within it. Shouldn't have shown that because I'm recording. Oh, I really shouldn't have shown that. Son of a. So when we get to functional groups, we've got a couple things going on here. So what we're going to do, let's clean up some of that context on the side. What you're seeing here are all the functional groups that I think you should memorize. Or have memorized. The pseudo problem with that is I don't know how well that's going to align or match to the quiz system. Right? Because the quiz system will probably ask a whole bunch of other functional groups because there's a whole hell of a lot more than what's on here. Okay? Why narrow it to this for what you need to memorize? It's OChem. Almost everything's going to be carbon-based. These are the most common ones that we'll work with. The rest of the other functional groups do appear and we'll probably work with them. For instance, the drawing that I've got in the upper right-hand corner is its own functional group. Okay, but we'll break it down into the component pieces here in a second. Okay. These are the most common ones, the most likely ones that you should be able to nail down. These are going to be ones that you're going to be responsible for naming, whereas the one that I've drawn in is not one that I would expect you to go through and name. Okay? Either as a structure or as a functional group. Okay? But what I do want you to be able to do is to call out what things are functional groups. Okay? And to recognize those patterns. Does that kind of make sense? Okay. So something that could help would be a more complete list of functional groups. Okay? You got a computer in front of you, right? Can you send me an email and be like, you need to do a better job giving me a list of functional groups?
Well, I think like the smaller list is, I mean, if those are like the main ones we're using, but I have a hard time like identifying some of them in
Yep.
simplified structure.
Yep.
It was like a molecule with a sulfur in it, and I kind of zeroed in on the sulfur, and it was like, I have a functional group with the sulfur.
Well, because there's no functional group with a sulfur here, because you're looking at an incomplete list. So I would argue that's why you should ask for what's a more complete list of functional groups. Because in this particular case, that instructor wanted to ask all the functional groups and probably had a significantly larger list. Okay? Some people have more emphasis than others to memorizing larger pieces. I would prefer that you can recognize the reactivity of a structure instead of knowing its name. Okay? So it's a give and take. Being able to reference the name becomes helpful, but it's not a requirement, particularly for this class. Does that make sense? So I will give you a more complete list of functional groups, and we'll walk through how we can make or identify functional groups within this structure. Okay? So, can I do it? I'm going to make a modification. Let's make it a little bit easier at first. Let's do that. Okay. So if I look at this structure, what functional groups do I see? Say again? Okay, where do you see the amine? Okay, we have a nitrogen, and so we could look at our pattern here. Amine, nitrogen goes out to, we're going to be bonded likely to a carbon, but even that is questionable. And then it says carbon, comma, hydrogen. Why does it say carbon, comma, hydrogen? It could be either or. Okay? And officially that can be either or as well. Okay? So we can look at NH3 and refer to it as an amine as well. Okay? So when we look to this structure, we've got the nitrogen. That should help us out. That nitrogen's connected to a hydrogen, carbon, carbon. Those are all single bonds, okay, or sigma bonds. We're looking at an amine. Okay? What other functional groups do you see? We see an alkene. So if we go to our alkenes, over here, we're looking at that pi bond. That's now an alkene. Okay? Based off of what I've seen within the context of the functional group quiz, this molecule would not be asked. Why not? Say again? There's two very likely functional groups. Okay? And there's another issue that's going to potentially pop up. This is one that you should, I submitted it, it said I was wrong. Can you please look at it? Okay. I wrote alkenes. Is that more than one alkene?
Yeah.
Or is that only one alkene? Is the name plural or is the name singular? Any quiz that has spelling even remotely within it is really hard to deal with, which is why if you think you're like, nah, I think I know, just send me an email, let me look at it. Okay? It is one, regardless of whether you send me an email, at some point I will look through everybody's and be like, did you just spell it wrong? Did you write, in fact, alkenes? Or maybe you were just super irritated at me, of course. And you decided to all cap it. Okay? How is it keyed? Anything that involves any kind of typing is going to have problems with that. Okay? Which brings up a good point, because I think I did include it in the assignment. There's a nomenclature one. Okay? And if you haven't started looking at the nomenclature, is that next week or this week? Nomenclature this week? Okay. Nomenclature has dashes and spaces and commas. And do you include a dash or a parenthesis or a comma? Should I have a space? Should I not have a space? Okay? Yes, there's a rule. And your instructor doesn't know it. Okay? Because it's not important. It's not relevant to really need to know the name. Why do we have names? Someone said it. To identify the molecule. So I could communicate that molecule to someone across the world. They could read the name and be like, oh, that means you're looking at this structure. What can I do now? Just draw the motherfucking structure and send a picture. Like, ta-da! Naming is an archaic system that makes a lot of sense for some select systems, but it's way overblown its value. Okay? To the point where I tried and failed miserably, okay, at trying to remove it from the curriculum. Okay? I got a lot of blowback for that one. Where it's like, no, you can't do that. Nomenclature is the greatest thing ever. I talk about nomenclature all the time. And I was like, and how do your students do? Like, oh, they suck at it. They're so bad and awful. They're like, well, how do you like point to a molecule and tell them what structure to look at? I was like, I point to the molecule and tell them what structure to look at. How do you tell them what structure you're talking about? I was like, oh, I point to it. And I was like, okay. You don't use the name, right? No, I don't use the name. Why not? Oh, I guess because students don't have... Yeah, the entire nomenclature system is kind of BS. Okay? So, are you responsible for it? Yeah, I'm sorry, you are. Okay? But we keep the level of intensity really, 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 really low. Okay? Is the specs quiz going to be a... being asked partial charges? Tell me what you do. And if you're like, I have no clue, that's fine.
I would just say assume, right?
Okay.
You're gonna hate me for this, but I'm just gonna be like,
I'm an ass all the time.
oxygen is the most electronegative, so
Wait, let's back away. You're assuming oxygen is the most
Well,
electronegative?
no, it is.
Okay, thank you. Yeah.
So I'm gonna assume that's got a partial charge of negative.
Does oxygen have a partial charge of negative?
Not in this one.
Okay, so there's a whole lot more going on in your head that you aren't putting out on paper. How did it become a partial charge? I should probably leave that one alone. It is very electronegative. Why is the bottom one not partially charged? Okay, I heard it, don't know what's happening. Let's push on this. What we're talking about is our electrons can move around. So when we talk about resonance, our electrons can move places, and we could assign formal charges. There's another concept that can happen, where the electrons don't literally move to an atom, but they're more inclined to lean that way a little bit. And because they're more inclined to lean that way a little bit, that part of the atom starts to carry a charge. Right? So if we looked at a heat map distribution, okay, throughout the class about where everybody was sitting, you might notice that Gavin's probably sitting a whole lot closer to the desk because I keep coming up and kicking his chair, and he's probably getting pissed at me. Whereas you all are able to spread back a little bit. So you could look at that as a heat map of where he's located. We're doing the same thing with electrons. Where are those electrons in that molecule dispersing themselves? Okay? And you picked the perfect system. Oxygen is very electronegative. So what does oxygen do? It pulls the electrons towards it. As it pulls electrons towards it, it has more electrons than it is capable of holding, which means it starts to become charged. Okay? It's not formally charged because we didn't put the electrons on it. We just said, just get kind of close. Okay? And as they get a little closer, we generate a partial charge. So what we want to do is acknowledge those partial charges because that can help us understand something about the reactivity of that molecule. So oxygen being electronegative, is going to start to pull on electrons. What electrons is it pulling on? Is it pulling on these electrons? Why not? They're not directly bonded to it. Officially, it is pulling on them, but it's relatively weak. Where our biggest pull is located is in the bonds immediately next door. Electronegativity is the ability to attract bonding electrons. So what I care about is these bonds. And since oxygen is more electronegative than carbon, this is why the bottom structure doesn't generate a partial charge, because oxygen bonded to oxygen, there is no difference in electronegativity. The oxygen starts to suck those bonding electrons a little bit away from the carbons, which means the oxygen starts to carry a partial negative. What happens to the carbons? They've now started to lose some of those electrons and start to become partially positive.
I just can't think of the structure off the top of my head, but like in one of the tests it was saying, oh, what's the